So friction is a force that opposes the motion of two surfaces that are in contact with each other. Most of this year so far, we have ignored friction, but in the last chapter, when we were summing forces and thinking about net forces and so on, we did start to introduce the idea that if there is friction, we have to overcome it. There are really two types of friction, static friction and kinetic friction. Static friction is the force exerted on one surface by another when there's no motion between the two surfaces. So for example, if you're going to have to move a couch, think about pushing on that couch and pushing hard enough to the point where it just starts to move. When you have achieved that, when you have pushed and pushed and pushed and it isn't moving yet, you are pushing against static friction. When you just overcome static friction, that's the point when it is allowing you to just start to get it moving. Once the couch starts to move, it switches from being static friction to being kinetic friction, because kinetic friction is exerted on a surface by another when the two surfaces are rubbing against each other. So when you have the couch sliding across the floor, it's in motion, you have kinetic friction. Now, generally speaking, static friction is greater than kinetic friction. It is harder to get it started moving than it is to keep it moving. So why friction? Why is there friction? Well, no matter what we do, there is no way to overcome friction because there's no way to make a surface so smooth that there aren't any tiny little irregularities for one object to get stuck as it moves across another. Now, there are things that we can do to reduce it. We can sand things very smooth. They can machine them to be very, very smooth. But when you look at it at the microscopic level, no matter what you do, there are little hills and valleys or ridges on every surface. In addition to that, even on very smooth surfaces, the atoms can become so close together that there's an actual electrical force of attraction between them. And so no matter what, there is friction. Doesn't matter how smooth the surface, it only matters that there are two surfaces. So we tend to think of that as, I'm sliding my feet across the floor, the car is driving on the road. But remember also that a form of friction would be air resistance as well. So how much friction will there be? We know from our life experiences that the amount of friction really depends largely on what the surfaces are. So if you are sliding a couch across the carpet, you may find it harder than if you are sliding the couch across a tile floor. The difference in the textures makes a difference. That leads us to this graph. Okay, so it shouldn't be too surprising to see that if we were moving a block of wood along sandpaper, that the amount of friction would be greater than if we are moving it over a rough table, and even far greater than if we were moving it along a highly polished table. But if you take a look at this graph, the normal force is plotted on the x-axis versus kinetic friction. So not only do the two surfaces, or the three surfaces, compare to each other in terms of sandpaper having more friction than the rough table, which has more friction than the polished table. But as we move from left to right, we notice that as the normal force increases, so does the amount of kinetic friction. Well, what's the normal force? We haven't really mentioned it before, but I think you know what a normal force is because in a way we have talked about it before. If I sit down on the chair and the chair is able to hold me up, which cross your fingers, it does, that means that I'm pushing on the chair and the chair is pushing on me, right? Newton's third law. If I lean against the wall and put my weight into the wall pushes back with a force equal to that. That force is a normal force, the pushback force, you could think of it as. So if we're thinking about normal force, being I've placed a block of wood on the table, the normal force is equal and opposite of the weight of the object. So to find the normal force, really all we're doing is finding the weight of the object. So the normal force is mass times gravity. So when we look at this graph, it turns out that the slope of the line of the graph is something known as coefficient of kinetic friction. It is a relationship between the normal force and the amount of friction associated with it. So the slope of any one of these lines is going to be called the coefficient of kinetic friction. And since we are taking a force and dividing by another force, the units cancel and the coefficient of friction has no unit at all. We label the coefficient of kinetic friction mu k. To find the force of friction, it depends on the coefficient, this multiplier, and the amount of normal force. So the force of friction is equal to mu k times Fn, or we could say mu k mg, since the normal force is equal to the weight. In the same way, the coefficient of static friction exists, and we have a mu s. So the force of friction, static friction, is mu s times the normal force, or mu s mg. This chart gives us an idea of how the coefficients of static friction and kinetic friction compare when we are looking at two different surfaces in contact. So cast iron rubbing over cast iron, glass rubbing on glass, non-stick coating on steel, and so on. And what you can see the general rule to be is that the coefficient of static friction between these surfaces is greater than the coefficient of kinetic friction. So how do we use this? Well, very simply, if we are looking for the amount of force that is exerted, we just have to find the force normal, or mg, times the coefficient of friction. So if a child is dragging this heavy rubber-soled shoe across a sidewalk at a constant speed, and the shoe has a mass of 1.56 kilograms and the coefficient of friction is 0.65, what's the force exerted by the child? Well, first of all, if we're moving at a constant speed and there is no acceleration, what that means is this child is applying a force equal and opposite of the force of friction. Remember that any time that there is no acceleration, we know that means that the forces are balanced. The other thing that is probably a little strange about this story is that the child must be dragging the shoelaces horizontally to the ground, horizontally to the sidewalk, because they're not talking about any kind of angle here. So in order to drag the shoe, we have to apply a force that is equal and opposite of friction, and friction is going to act parallel to the sidewalk. So we just plug and play. So mu k mg means we're going to take 0.65 times the mass of the shoe, 1.56 kilograms times g, which is 9.8, and we find out that this child would have to supply 9.9 newtons of force to drag this shoe horizontally. How would we rearrange the expression if we're looking for the coefficient of friction? So we have this 15 kilogram box and it is pulled by 70 newtons of force across the floor. Again, that must be a horizontal force. But this time the box accelerates and we want to find the coefficient of friction. Well, remember that when we sum forces, if we want to accelerate, we're not only going to have to apply a force equal to the force of friction, we're going to have to supply some additional force to cause that acceleration. So our net force is equal to the force of friction plus some force allowing us to accelerate. So if we substitute here, the force of friction is mu k mg. The force causing the acceleration is found by using ma. And we rearrange. So I would subtract ma from the net force, and that would give me mu k mg. If I'm solving for mu k, I have to divide by mg. Plugging it all in, the amount of force applied is 75 newtons minus ma, which would be 15 kilograms times 3 meters per second squared, divided by mg, so 15 times 9.8, and we get a coefficient of friction of 0.2. No unit. Coefficients of frictions do not have units. One more example. So those problems have all worked with horizontal forces. We found out in the last unit that, of course, we don't always pull in the horizontal direction to move something horizontally. So if we look at a story where we have somebody pulling on a sled and the rope is making an angle, how are we going to solve for that? Well, we have, in this case, a combined mass of 33 kilograms, a rope making a 51-degree angle, a coefficient of friction of 0.15, and we want to know how much force has to be applied along the rope, and there is acceleration of 1.5. So first of all, we need to find our net force, the amount of force in the x direction that would overcome friction and provide enough force for acceleration. So similar to the last problem, we have mu k mg plus ma. So if we find this force in the x direction, 0.15 times 33 times 9.8 plus 33 times 1.5, and we find out that we would have to apply 98.01 newtons of force, but that would have to happen in the x direction. If we are pulling at an angle, the force in the x direction then would be down here, and we would make a right triangle using the rope as the hypotenuse of our triangle. So to find the force of pull in the rope, we're going to take our adjacent side and divide by the cosine of the angle. So we're taking fx and dividing by the cosine of our angle. So 98.01 newtons divided by the cosine of 51, and 155.7 newtons of force, with sig figs 160 newtons of force, must be pulled through that rope in order to cause that acceleration of the sled.